you know that if I hook this inductor right here up to a battery, it will behave initially as a bad battery. It doesn't want to have any current in it, and so it rejects the current coming in and pushes it back the other way, because as the field in it changes, it induces, the inductor itself induces a voltage the other direction that tries to not let the current within itself change so that the flux through it doesn't change. Of course, it'd be a little bit more meaningful if we had like a real toroidal inductor or solenoidal inductor like this, something practical. But let's draw a little sketch of that. So I'm saying that if I hook a battery up, let's put a little switch in the circuit so we can talk about this actually happening at some time, to an inductor, that's the circuit symbol for an inductor, then we will get a current that looks like this. Let's see if I can get you some current as a function of time. Current will start at 0 and try to get more and more and more and asymptotically approach this current. Wait a second, with no resistor in there, that current would go to infinity. So I will give you a resistor. There we go. That's how it can asymptotically approach a value. We've got that resistor there. And that current that it's approaching is when the inductor appears as a line in the circuit, a short in the circuit. So that that current right there would be the voltage of the battery divided by the resistance of the resistor. Of course, if the resistor is in fact 0, then that voltage, the ultimate voltage, would be infinite, and we would go up as a straight line. If no resistor, we would just go like that, and we could put more and more and more current into this sucker, and that's how you might make an electromagnet, for instance. You just hook up a battery, a DC voltage source, to a coil of wire, and the field gets bigger, and then at some point you short out the battery, and the current just keeps going. You wouldn't want to do this if there is some resistance, though, because if there's a little bit of resistance, that energy will just be dissipated out through the resistor. But if you've got yourself a superconductor, then you could put some field inside this inductor, and then you could say that the energy density in the inductor would just be 1/2, what do you get? 1/2 mu naught times the magnetic field square. It's probably down in the denominator. Let's put mu naught in the denominator. All right, then what if we hook up our inductor to an alternating source? Because this is similar to charging a capacitor. You thinking what I'm thinking? The capacitor was like, oh, current's going to go like this, and eventually stop going through the capacitor. But when we hook up an inductor, current's going to go like this, and eventually reach a steady state. So you see how, again, capacitors, this is capacitor upon closing the switch, and this is the current through the inductor upon closing the switch. They are, again, sort of exact opposites or analogs to one another in exactly the opposite way. So now we're going to go to a slightly more pleasant situation. Let's go to, I mean, it's more beautiful anyway. We've got this alternating voltage source, and it's putting out Vmax sometimes, putting out 0 at other times, etc. And I'm going to hook this sucker up to an inductor. And then I'm going to close my circuit. And my plan is now to try to figure out what the voltage and current are doing as a function of time. So initially, it's going to try to make a current go through here. And the inductor will be like, no, I don't really want a current to go through there. But it gets used to it tries to get, does it ever though, if there's no resistance in here? No, eventually, it's pushing, and some current starts to trickle through here. But by that time, this guy has switched voltage. So there's a derivative in here, remember? Like, what if I tell you the induced voltage is, well, it's just d flux dt, right? That's the induced voltage on the inductor. And we know, I mean, this is really just the definition of inductance. This is the same thing as the derivative of ddt of the inductance times the current that's going through the inductor. Oh boy. All right, so assuming that my inductor is a physical thing that's just sitting there, its physical characteristics tell us the inductance of the thing. So I can go to the next line and say, what am I going to say? I'm going to say that L pulls out. And then I'm going to plug in the derivative of the current as a function of time, because I know what that current is doing. That current as a function of time is doing that sine thing as we had before. This is going to be the inductance times d dt of the maximum current through the inductor times sine of omega t. That's just the way we show the sign dependence, the sinusoidal nature of this power supply, which is giving us a sinusoidal current in here. But the current is not in phase with the voltage again. This is no resistor, so we don't expect it to have maximum current when there is maximum voltage and zero current when there's zero voltage. In fact, the current is going to be maximum when the voltage is zero, and the current's going to be minimum when the voltage is zero. And the current's going to be zero when the voltage is maximum, and the current's going to be zero when the voltage is minimum. That's what derivatives of sinusoidal graphs give you. But let's just jump into it here. I know that, well, I can take the derivative of that, no problem at all. I'm going to get the inductance times I max times the cosine of omega t, and chain rule says that I get myself an omega falling out of there. All right, so I can clean that up a little bit. I get omega times the inductance times the maximum current, and then instead of writing cosine of omega t, I actually know that that's the same thing as sine of omega t plus a phase shift. And I want to remind you that the capacitor had a very similar sort of structure. As I recall, it had something like, well, the voltage on the capacitor, oh dang. Let me see if I can remember that just off the top of my head. I think it had something to do with omega, but omega was in the denominator. We had capacitance divided by omega? No, it was 1 over capacitance and omega, and then, oh, what was it? Wasn't it? Yeah, I think, times I max times the sine of omega t minus pi over 2. So the phase shift was different because we had a minus sign out front. This was what we got for the capacitor's voltage, and this is what we have for the inductor's voltage. Notice omega's in the top here, omega's in the denominator there, inductance is in the top here, inductance is in the denominator that. Oh my goodness, this is so funky. I'm next going to say this kind of looks like an Ohm's law sort of thing. V is IR. So I see that my maximum, if I just want to think about maxima, then the sign's going to give me 1, right? So I'm going to say that the maximum voltage is the maximum current times this thing right here. And that is what, guess what? I'm going to define that it's I max times the capacitive reactance. Just kidding, the inductive reactance, X sub L. And of course, we're going to follow all the same procedures as we did for the previous discussion. I've got this equation right here, and I need to define inductive reactance. Inductive reactance is simply omega times the inductance of my inductor. So that means that the bigger the inductor you have, the more it reacts with the circuit. That's the opposite of a capacitor. Remember capacitive reactance? We said capacitive reactance was 1 over omega times capacitance. And we found that the bigger the capacitance and the higher the frequency, the less the capacitor was a problem. Because the capacitor would, if you're going at really high frequencies, it'll never fully charge. And if it's a really big capacitor, it'll never fully charge. That's the exact opposite performance as an inductor, because if you have a big inductor, it's going to take an enormous amount of oomph to get that sucker to change states because of that derivative. And if you have a really big frequency, it's going to want to change, it's going to try, the power supply is going to try to change the direction of the magnetic field really quickly, and the inductor will get pissed. The inductor just doesn't like that. So these guys are justifiably completely backwards from one another, and I love it. So let's make a graph now. We can go back to a phasor, and we'll have y here, and X here, you should really do some simulations. I'm going to remind you that a resistor is going to have the voltage and the current in phase with one another. So they are completely in line, and the resistor dissipates no power here, and maximum power there, and no power there. It's just I times V, right? And minimum power there, and no power there. Did I mean to say minimum power? It doesn't have a direction. The power will be dissipated a lot here and a lot here. The Y component of where the phasor is what matters. And then the capacitor. See, the capacitor has the voltage and current always 90 degrees out of phase with each other. So it will, in fact, never dissipate power. It's dissipating, well, let's see. I guess we're charging the capacitor during this time right here where the voltage and current are both positive. And then at this point, boom, the current is negative and the voltage is positive. So we're discharging the capacitor. Discharge, 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 discharge. And then at this moment, boom, we're charging the capacitor again because they're both negative. We're charging the capacitor negatively. And then in this quadrant, boom, we are discharging the capacitor in because I've got positive current and negative voltage. So you see, at actually twice the frequency, we're charging and discharging the capacitor. It's twice the frequency of the drive. Twice the frequency of the phasors revolution. And I'm going to leave the capacitor on here so that you can look at it. Look at the distinction between the capacitor and the inductor phasor diagrams. We've got, oh shoot, I didn't label that sucker. This is current, and I need a green pen. I got one, don't worry. This is the maximum current on the inductor. The maximum current on the inductor is again 90 degrees out of phase, but remember, we had plus pi over 2, that's 90 degrees right here, for the voltage of an inductor, and minus pi over 2 for the voltage on a capacitor. All right, so the fact that it's the opposite direction shouldn't surprise anybody. Maybe we can intuit it further also. But let's think about power in the inductor. We're going to be, let's see, putting some energy into the inductor here. Let's say we start out with maximum voltage. Let's make ourselves a graph. I'm going to graph the voltage and current as a function of time through an inductor. And I'm going to start out with maximum voltage, go down to minimum voltage, and then maximum voltage. And this is my power supply. My power supply is just doing the best it can. It's trying to make the flux change through an inductor, and the inductor's entire reason for being is not to let the flux change. So what we've got is, you know that the voltage is the derivative of the change in flux. So the current is going to be 0, but maximally changing here. And it'll be 0 here, but maximally changing, and here, and here. And so initially, there is no current. If the voltage is very high, there's no current, but the current begins to ramp up. It's like, okay, fine, I'll get used to it and give you a current. And then, oh shoot, it's gonna stop increasing the current here. The green graph will be current. It's going to stop increasing the current because now the voltage is the other direction. And so the current begins to decrease. And as at the instant when the voltage is absolute bare minimum, that's when this sucker is changing the most. Well, I guess they're derivatives of each other, right? With a minus sign. Be careful. And this goes like that. And that's what 90 degrees out of phase really means. This guy's supposed to be there at that time right here, and then back up to here. Good. So can you tell me which one is leading? Again, I think you might be mistaken in your initial assessment of which one's leading. As we go through in time, which one of these seems to be making the other one make its changes? See, the way I see it, the voltage drops. The voltage drops to 0, and then the current's like, okay, I'll go down to 0. And then the voltage hits a minimum, and the current's like, okay, fine, I'll get to a minimum. So while it looks like the current is leading, I would say that the voltage, in fact, is leading. Voltage leads current by 1/4 cycle, or pi by 2. Or 90 degrees. I don't care how you say it, but the voltage is ahead of the current, and that's because of the definition of inductance and essentially Faraday's law of magnetic induction. The next thing we'll do is we'll put a capacitor and an inductor into the same circuit and see how they interact, and you will find pure beauty. Go back and watch the Tacoma Narrows Bridge video. Watch that sucker fall down before you watch my next video. Within itself change so that the flux through it doesn't change. Of course, it'd be a little bit more meaningful if we had like a real toroidal inductor or solenoidal inductor like this, something practical. But let's draw a little sketch of that. So I'm saying that if I hook a battery up, let's put a little switch in the circuit so we can talk about this actually happening at some time, to an inductor. That's the circuit symbol for an inductor. Got that resistor there. And that current that it's approaching is when the inductor appears as a line in the circuit, a short in the circuit. So that that current right there would be the voltage of the battery divided by the resistance of the resistor. Of course, if the resistor is in fact 0, then that voltage, the ultimate voltage, would be infinite, and we would go up as a straight line if no resistor. You know that if I hook this inductor right here up to a battery, it will behave initially as a bad battery. It doesn't want to have any current in it, and so it rejects the current coming in and pushes it back the other way, because as the field in it changes, it induces, the inductor itself induces a voltage the other direction that tries to not let the current. No resistor, we would just go like that, and we could put more and more and more current into this sucker, and that's how you might make an electromagnet, for instance. You just hook up a battery, a DC voltage source, to a coil of wire, and the field gets bigger, 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 and then at some point you short out the battery, and the current just keeps going. You wouldn't want to do this if there is some resistance, though, because if there's a little bit of resistance, that energy will just be there. Then we will get a current that looks like this. Let's see if I can get you some current as a function of time. Current will start at 0 and try to get more and more and more and asymptotically approach this current. Wait a second, with no resistor in there, that current would go to infinity. So I will give you a resistor. There we go. That's how it can asymptotically approach a value.